Two random variables walked into a bar. They thought they were being discreet, but I heard their chatter continuously. And since I'm not a fan of continuous chatter, we're going to start with discrete random variables. And hopefully you got that joke. So, what's fair? You and a friend wager on heads or tails. If he bets $1 on heads, what is a fair wager for you to make on tails? Well, it's fair if you both come out even over the long run. That is what fair is. Since both seem equally likely, it intuitively seems fair that you bet $1 on tails. So let's go ahead and do the math. We have a table here with heads and tails for the outcome. The payout is that you lose $1. If heads comes up, and you gain $1 if tails comes up. The probability for both of these is 0.5. They should add up to 1. Then we're going to go ahead and multiply each of these for their expected payouts. And I'm doing 100 plays. So 100 times 0.5 times -1 is -$50. And 100 times 0.5 times 1 is $50. When I add those two, I get 0. And that seems fair. Now let's have a different game. You and a friend wager on a die roll. If you bet $1 on rolling a 6, what is a fair wager for him to make on the rest of the outcomes? So he wins if a 1 to 5 comes up. A $1 bet doesn't seem fair because most of the times you expect to lose. So we'll go ahead and do the math again. Our outcomes are either you losing with a 1 to 5 or you winning with a 6. If you lose, you lost $1, and the probability of that is 5/6. The probability of you winning is 1/6. So the expected playout for 60 plays. So it'd be 60 times this amount times the probability. Oh, those add up to 1, by the way, is -$50. If I go 60 times 1/6 times question mark, it's like 10 times question mark. So I should get $0 if it's fair. 10 times what would give me an amount to make this total 0? Well, if I got positive 50 here, then my total expected value would be 0. So $5 would seem like a fair bet on a 1 to 5 to match the $1 on the 6 bet, because you expect to lose 50 and gain 50 over 60 plays, so you would come out even. So what are random variables? Basically, they're the outcomes of like +1 or -1 or +5. They're typically denoted by X, Y, or Z, or some other capital letter. Now, a random variable assumes any of several different values as a result of some random event. A discrete random variable can just take on specific values. It can't take on a continuous range like continuous random variables. Discrete random variables might be like payouts, whereas continuous random variable, maybe that's like a weight, which could be anywhere. Applications include games of chance, insurance, the stock market, and so forth. So one thing we use when analyzing this is a probability model, and that's a collection of all outcomes and associated probabilities. Some common ways to display a probability distribution for a discrete random variable is with tables, tree diagrams, and/or a formula. I personally prefer either tables or tree diagrams. Sometimes if it's complicated, the tree diagrams can really help you figure it out. So we're going to consider a die game where there are no points for rolling a 1, 2, or 3, 5 points for rolling a 4 or 5, and 50 points for rolling a 6. So my outcomes are 1, 2, 3, 4, or 5, or 6. The variable I'm really going to keep track of is the number of points. So this is my random variable X. I can get 0, 5, or 50. The probability of rolling a 1, 2, or 3 is 3/6 or 0.5. A 4 or 5 is 2 out of 6 or 0.3 bar. And rolling a 6 is 1 out of 6, which is roughly 0.167. Note that the probability of 6 is the same as the probability of X equals 6. That's typically the notation we use. Make sure your probabilities add up to 100% or 1. So let's take a look at flipping a coin 3 times. What is the probability distribution for the number of tails? So here I've drawn all 3 flips. And what I've done is I've counted on the outcome the number of tails. So if I go heads, 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 0 tails. Heads, heads, tails is 1 tail. Heads, tails, heads, that's 1 tail. Heads, tails, tails, that's 2 tails. So here are all of my outcomes. 0, 1, 2. The maximum number of tails is 3. Now the probabilities, luckily each one of these branches, I don't really have to draw the probabilities because they're equally likely. So I just have to count the total outcomes, of which there are 8. So the probability of getting 0 tails is 1/8. And 1 tail is 3 outcomes out of 8. 2 tails is also 3 outcomes out of 8. And 3 tails is 1 out of 8. So the total should be 1. So how do we figure out the expected value from this table? Well, an expected value, this is a theoretical long-run average value. It's the center of the model. It's not what will happen, but it's what we expect to happen in the long run. We denote it by E of x and sometimes mu when talking about population mean. It can be found by summing the products of variable values and their associated probabilities, and this is the formula. So let's get back to those coins. We already have the probabilities, which we filled in previously. So I'm going to go 0 times 1/8, which is 0. 1 times 3/8 is 3/8. Now I have 6/8 and 3/8. When I add all of these together, I get 12/8, or 1.5. So the expected number of tails is 1.5. But we don't really expect to get 1.5 tails on 3 flips. That's impossible. But on average, we expect to get 1.5 tails on 3 flips. So if we conducted many experiments of 3 flips, the average is 1.5 tails. We would never see 1.5 tails on 3 flips in reality. All right, let's go ahead and get back to a dice game, and we're going to go ahead and do expected value again. So we have 1, 2, or 3, no points. So it's the same game we had before. I filled in the probabilities from before. And we're going to multiply the points times the probabilities. And when you add them up and get the expected value is actually 10. Now the payout will probably never be 10. You never get exactly 10 points on any one turn. But if you average many turns, you would expect to average 10. So let's go ahead now and visit variance and standard deviation. So we've already dealt with standard deviation before when we looked at, calculating averages and standard deviation and variance. It works very similarly here. So we've got the example of the die, and you probably remember this x minus mu squared. Instead of multiplying by a frequency here, the weight is the probability, which kind of makes sense. So we're going to go ahead and use this formula. By the way, this is on your math chart. Sigma squared equals the variance of x, which is x minus the mean squared times the probability of x. So when I go x minus the mean squared times that, I get 50. 5 minus 10 squared times 0.33. 50 minus 10 squared times 0.167. And you can see some of these have a much bigger influence on the final variance, which is 324.992, or about 325. Now remember, sigma is the standard deviation of x, and this stands for population, this is for sample, and we find that by taking the square root of variance of x. And in this case, our sigma is roughly 18.03. Now, of course, the amazing thing is the calculators are really good at doing this. So we're going to start by creating list 1 for the outcomes by hitting edit and enter your outcomes there, and we've got them in. And after we do that, we're going to create list 2 for the probabilities. So we'll go ahead and put those there. You can actually put fractions in. You don't have to put the decimals in, but if you know the decimals, that's fine. So I could have actually said like 3 divided by 8, and it would have given me the 0.375. All right. Press Stat, Calc, and 1var Stats, just like we did before. Make sure you get list 1. If you have the old layout and you have to do the list in a line, you're going to have to put a comma and then select list 2. If you have the more modern calculator, you're going to see this under data and this under frequency, and you're just going to press enter and it will give you the statistics. careful, the calculator usually uses x bar instead of mu, but it does use sigma of x properly.